Well, wonderful turnout. So I was telling some folks all we did is walk down the street and just say, maths, maths, and people just started coming. This is what happens. This happens all the time. Right, so I guess maybe a little bit about me, so this will probably be difficult to read for those of you way in the back. But so my background is, I'm from New Mexico. Does anyone know where that is? We've got a handful of people. Yes, actually there is a New Mexico. Yes, it's the part of Mexico that's in America. Right. It's very mountainous, deserty, it sun shines a lot, doesn't rain very much, so that's where I'm from, and that's where I did my studies. I have a bachelor's in applied maths, I did my master's in applied maths, and then I worked at a place called Sandia National Laboratories, which sits in my hometown of Albuquerque, New Mexico. I was part of the computational biology department there, which means I banged my head on a keyboard all day. Does anyone else do that? Yeah, banging my head on a keyboard, right? Well, at some point I had to do a PhD, so I came to New Zealand. At the University of Auckland, there's a world-famous mathematical biologist, James Sneed. He's the co-author of my textbook, Mathematical Physiology. So I came to study with him because science is a lot about who's your daddy. Here's my daddy. Right? I did some postdocs, so I was in the math department and in bioengineering. Did a stint up at Massey University, and now I'm back at Auckland Bioengineering, and currently I'm modeling the uterus. Thank goodness for the uterus, or none of us would be here. Meanwhile, I do get to lecture math once in a while. I don't just do research. I enjoy torturing, teaching math. Right? So it's a fun and, I mean, it's difficult. You always have to push people away. We don't have enough room for everyone that loves math so much. You'll have to wait. This happens all the time. And partly because when I give exams, we ask very simple questions. Where is X? Oh, it's right there. Right? Or when you're simplifying things, oh, obviously 6 equals 6. Just cancel the ends and away you go. Right? So also if you have these patterns, if lim 8 blah 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 equals 8 sideways, then lim 5 blah 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 equals 5 sideways. Math. Of course, some people, they express their frustration. Some of the artwork that I get in my classes is quite entertaining. Math can also be challenging. So these are derivations that I put in a paper. There's a test at the end of the session. Please write this down. I'm kidding. Right? So this is actually from a paper that I did on spatial distributions of malaria in African villages. And when my colleague and I were writing these expressions, one word kept coming to mind. Does anyone know what that word is? Anyone want to guess?
Rising.
Ugly. So ugly. This was awful. These were the simple expressions. And we had to type these up and put them into a paper and get them published. And the reviewers came back and they said, you survived, well done. Move on with your life. So if math can be frustrating and challenging and ugly, well, why do it? Why bother? Why do this thing called math? Are we just masochistic? All golden and lovely in the sunset it blazed, with walls, temples, colonnades, and arched bridges of veined marble, silver basined fountains of prismatic spray in broad squares, and perfumed gardens, and wide streets marching between delicate trees and blossom-laden urns, and ivory statues in gleaming rows, while on steep northward slopes climbed tiers of red roofs, and old peaked gables harboring little lanes of grassy cobbles. It was a fever of the gods, a fanfare of supernal trumpets, and a clash of immortal cymbals. Mystery hung about it, as if clouds about a fabulous, unvisited mountain. Mystery, the unknown. We are curious beings. That is the beginning of a book by H.P. Lovecraft, The Dream Quest of Unknown Cadet. Also, incidentally, it's the beginning of my PhD dissertation. Mystery, curiosity. How does the world work? The world is full of patterns, full of interesting things. How did it come this way? Why is it so structured? Why can we understand it? Math is used every day by someone, somewhere, in some way. Are there any nurses in the room? Any nurses in there? Wait, nurse. Oh, she's hiding. Right? So you use maths to make sure you don't kill someone with this dose, right? Got to give you the right amount. A little calculation there. Any builders in the room? Any builders? Engineers? Architects? Nah, that's right? Imagine if this building didn't have right angles in it. Wow. Seems a little bit off. Geometry. Also, when you need to get change. Does anyone use cash anymore? Yeah, cash. I still pick up coins when I find them on the ground. Ooh, 50 cents, cool. Needs can drive mathematical development. This is an excavation of an Indian temple. A temple that was built apparently between 200 BC and 100 AD. This temple was very specific in how it was built. Precisely arranged geometric requirements for these tiles, for these stones. Numbers indicated the order in which the bricks had to be consecrated with mantras. The first layer, there are 38 squares, 58 rectangles, and 104 triangles. They needed precise descriptions of these geometric shapes. Needed to know their areas and their extents. How do we make these things? Out of reverence for their faith. Okay. So who came to a math talk and thought you weren't going to talk about maths? Thought that you weren't going to do some maths. Are you ready? 2 squares. One square is a side length A. The other side has a side length B. What are the areas of these guys? Oh, come on, we feel it. Come on. A squared and B squared. Yeah, I got this. Right? Confidence. Okay, let's see. I can slide these around, thanks to the power of PowerPoint, right? I can also assemble a new square out of these. What's the side length of this square? A plus B, right? Because I just stacked them that way. I did it that way, right? So I can take this, these little gray bits, I can carve them up. I can also take these gray bits who have sides length A and B, right? Those legs. I can take these things and shift them around, right? So I can move them. And once I rearrange that, I've made another square. Notice how the A squared plus B squared, the colored bits, right? And now these carved up bits, the gray bits, those diagonal lines, let's call those C. Does anyone see where this is going? Right? Those correspond to the C's over in the other square. If we fill that in, the colored bits are what? So I can delete the gray bits. This will make it clearer. So this is all that's left. Without the gray bits, what have I just proved? A squared plus B squared equals... Come on, with confidence. C squared, man. Yeah, that's the stuff. Oh, does this look familiar to anyone? What is this thing called? I hear silly people saying Pythagoras. Actually, this is the theorem of PowerPoint animations. Right? Right, but this thing has been discovered or invented many times. This is a cuneiform tablet from a school child from Babylon, circa 1800 BC. The Babylonians discovered this relationship a long time ago. The Chinese, the Indians, and then this Pythagoras fellow. That's the Greek guy, right? You've heard of him. The so-called Pythagoreans, who were the first to take up mathematics, fancied that the principles of mathematics were the principles of all things. When I say discovered, what do I mean? Like we're discovering some unknown continent, like Lewis and Clark here. Seeing mathematical rivers and mathematical mountains and mathematical valleys and mathematical bears. Run for your life. Right? Is that what it means? Or maybe it's just an invention, like Nikola Tesla, sitting underneath that very calming event over his head. Right? It's just an invention. Are we just making up this stuff? What is mathematics? Well, sometimes if I'm not sure what something is, I go to a dictionary. Let's see what the dictionary says. It says the abstract science of number, quantity, and space, either as abstract concepts, pure mathematics, or is applied to other disciplines such as physics and engineering, applied mathematics. And I find I often have to put an addendum to these, and relationships between them. Mathematics is really the study of relationships between quantities. A squared plus B squared equals C squared. Because you get better, more confidence. It'd be cool if, like, after this, you're just walking down the street, like, A squared plus B squared, C squared. See what people do. There's also a language of precision. The sum of the areas of the squares besides the length of a right triangle's legs is the same of the area of the square with the side length of the same right triangle's hypotenuse. That's the bit opposite the right angle of the triangle. Or A squared plus B squared plus C squared. Right? This is much more compact. It's less ambiguous, right? For specific triangles. Why does this work? Why does that relationship work? These have been philosophical problems for centuries, millennia. Some people think that mathematical entities exist, that they have an existence independent of human minds, like Homer's wandering around in mathematical land. Look out for the mathematical bears. Right? These entities inhabit a special world, a Platonic world. How do these Platonic entities, which do not have spatial or temporal characteristics, get in touch with our physical world? Alternatively, they're just inventions. There's a couple of subtypes of this fictionalism or inventions. Logicism, formalism, languageism. It's going with the ism pattern there. Logicism basically says that math statements are not necessarily true in the real world, but are true within the story of mathematics. Nothing but the systematic construction of complex deductive arguments. All of math can be derived entirely from logical laws. This is from the philosopher Sarukai. Languageism. Math is like English, but not. Right? A product of human imagination is grounded in our experience with the world and functions like a language. Beginning with numbers along with operations like addition, we can find a link between human experience, what we do and what we see, and the structure of the world around us and mathematics. Alternatively, it's just a game. Has anyone played a game and not played by the rules? You're not playing a game, right? Nothing but a set of rules and formal manipulations of symbols and terms according to these rules. There's no meanings attached to these objects, equations, operations. Mathematics is just a chess game. A chess game. That itself seems rather odd. These have problems. If it's realism, mathematical entities exist independently of the world and are just discovered, that suggests some pretty weird things. Maybe if I draw on a chalkboard a proper equation, we can dive through it and we can hang out with Homer that's checking out the mathematical bears. What do you think? Or maybe they're just inventions. Then why does it work? Mathematics has stunning predictive power about the real world. Not only that, we can do it. Why can we do it? Why are our brains so suitable for doing maths? Because everyone here does maths, right? We all calculate. How many people drove here? A lot of people, right? So when you're driving, do you see vectors on the road? Oh, we're going to die. Right? Oh, we're not going to die. That's a good short vector, right? Is that how you do it? Is that what you do when you're driving? No, probably not. But we do have the ability to perform sophisticated calculations. Right? Just interacting with the world is complicated, is complex. Particularly driving. Or playing ball. Like if I threw this to someone, they could probably catch it because of a very familiar thing called ballistic motion. We grew up in this gravitational field of the Earth. We're pretty familiar how things work. And also I've seen extraordinary calculations by people to avoid maths exams. Right? There's an order to the world around us. There's a logical structure. It suggested that this logical causal reality is key to our abilities to do mathematics. And from the evolutionary perspective, mathematics incorporates cognitive mechanisms which have evolved, like other biological mechanisms, by confrontation with reality and have become genetically fixed in the course of evolution. By Yehuda Raab and his paper discussing these things. We live in an environment that exhibits very predictable behavior. Relationships between force and action, consistently measurable quantity and extent. And evolution is proposed as the mechanism for creating this ability. The logical schemes and hypothetical representations are the same as the logical schemes in the coordination of actions, schemes that have been tested through eons of evolution and are genetically fixed. So these are very long ways to say that athletes are good mathematicians. Being able to interact in the real world is no different than doing math. Driving and deducing are the same thing. Do you believe that? Oh, what's it doing? It's like an aquarium pump is going on here. Can I tell you a story? It'll distract me from this strange machine over my head. Do you guys like stories? Can I tell you a story? Yeah. Okay. I've been in many math departments, and I met some interesting people. When I was at Sandy Labs, I should do the Bob the mathematician. There was a mathematician there named Bob. Bob was brilliant. I would see Bob, he would come in at night as I was leaving. It's like, what are you working on, Bob? Oh, polyhedral combinatorics. I don't know what that is, Bob. Have a nice night. Right? But Bob was brilliant at math, but he struggled in other areas of life. And we often had encounters with Bob that could be memorable. Let's put it that way. So one time, I went into work in the system and he called me in, hey, Shawn, I got a Bob story for you today. Okay, what did Bob do this time? So he detailed how Bob came in the office and he asked the sysadmin, the IT guy, do you know anything about the wheels on cars? Well, I guess so a bit. What do you mean? Well, can you come and look at my car? I think there's something wrong with the wheels in my car. It's not really my job description, Bob. He's like, okay, come have a look. So he goes outside and looks at Bob's car, and the tires were shredded because he'd been driving on flat tires, and the wheels were damaged. It's like, Bob, didn't you notice that your tires were flat and you were driving on them? Well, I thought something was wrong. Yeah. And so Bob's like, well, what do I do? I don't know what to do. He's like, well, you got to go get it fixed. You have to repair them and replace them, blah, blah, blah. I don't know what to do. Can you help me? So I was like, oh, Bob. So he arranged for a tow truck, and he went with him to get the tires and the wheels replaced and the whole bit and brought him back. And so I come along, and he's like, man, what a Bob story for today. Bob, he was a lovely guy, but he really struggled to function in certain ways. Driving and deducing are the same thing. This perspective conflates two very different ways of thinking, two different modes of thinking. And one of the oddities of human intelligence is that its level of advancement seems like a case of overkill. These higher intellectual functions are a world away from survival in the jungle. Most biologists believe the human brain has changed little over tens of thousands of years, which suggests that higher mental functions have lain, that's such a strange word, lain, largely dormant until recently. Yet if these functions were not explicitly manifested at the time they were selected, how were they selected? How can natural selection operate on a hidden ability? They're latent. What good are they for survival if you can't drive your car without destroying the wheels? Okay, enough of that fluff. Let's talk about math. Or do some math. Let's say I've got a square, side length x. His area is... Sometimes I ask really easy questions. The answer is right there, x squared. Come on with confidence. X squared. Yeah, you got it. Okay, sweet. I can compute the areas of this square, right? I can make a table of values for given a side length x. I can also make a graph. That's because we like to see these things. It's easier to see patterns from a graph. I can also ask you a question, a simple question. What side length x gives us 0 area? 0. And one of the easiest ways is just look at the graph. Where does this plot intersect the x-axis? You guys just told me, right? It's right there, Shawn. Yes, such a silly question. 0. You can also solve this thing. X squared equals 0, so that means x equals 0, right? Hooray, we did some math. Think about negative values, though. What if I extend this plot out to negative length? I can compute these numbers, right? I'm going to get this lovely shape. But what the heck is negative length? What does that mean? Have you guys been to the section of bunnies in the tool department where you open up the magical door? It's the black hole department. Cool, I got this negative length measuring tape. And then you go up to the front. Can I give you $- for this? Yeah, I haven't found that department yet. I'm looking for it. Negative length. It makes no sense, right? There is no such thing. Think about negative numbers, though. Do negative numbers themselves make sense? Does anyone encounter negative numbers every day in life? Good old credit, right? But also, if you're like a diver, you go below the ocean surface. Also, if you're freezing to death. Right? Welcome to negative numbers. So there's a context to them that gives them a meaning and that helps them to be reasonable. So since negative length doesn't make sense, for our mathematical model of area, we blot out the negative values. They don't make sense. Because this is our model of area. And it all hinges on, remember this stuff with signs? Remember primary school? So when you multiply a number by itself, what's the sign of the number? So I see someone say positive, yeah. Wow, so many eyeballs are just like, oh. Let's see, if I multiply a positive times a positive, what's the sign? Positive. If I multiply a negative times a negative, what's the sign? Positive. Positive. So if you multiply a number by itself, what comes out is always positive. That's why the parabola is pointing up, right? It's symmetry. If I want a negative number, can you multiply a number by itself and get negative? No. So to get negative, you have to have mixed signs. That's partly why this parabola is like this. And also, it destroys the input. So you don't know what you started with. But interestingly, negative numbers were rejected by Western mathematicians until about the 17th century. Does that seem odd? Maybe it's because they didn't have credit cards. Right? Okay. So let's do a little bit more math. Let's say we've got our square, x squared area, and we've got another area, side length 1, whose area is 1. And let's say that this area is a tax. Inland revenue is going to take a one area tax off everyone's highs, right? And thanks to negative numbers, they can do that, right? We can compute a table of values to see what values we have left over after they take tax out of our area highs. We can also plot a lovely graph. And I can ask you this question: what side length, x, breaks us even with I or D? 1. Well, you can look at it here, 1. You could also look at the graph to see, oh, where does it cross the x-axis? Right, so bang, it's like right there. Now I can also solve this thing, x squared minus 1 equals 0. Solve this, x equals 1, and everybody's happy. You just don't have as much area as you did, and now the government has everyone's area. Thank you, government. Okay, what if I flip the script, though? Instead of a tax, it's a refund. So you're getting an area. Woohoo! We have more area. We can make our table of values. I can also plot this thing. And I can ask you a question. What side length x means we're broke? Well, if I look there, what's going on there? I'm not sure what's going on there. But what if I solve this? X plus 1 equals 0, x equals minus 1. Is that right? Wait a minute, if I extend the parabola out, because I was saying that x equals minus 1, so I've shifted into negative land. That's getting into something weird, a negative area. Also, look to see, oh, so I compute those values, right? And so, is it crossing the x-axis? No, so is there a solution? So I've done something wrong. Any math teachers in the room? Right, math teachers? So did I do something wrong? Yeah. I forgot something, didn't I? This is partly why when I do derivations for research, I send it to my colleague. Can you check this for me? I probably did something stupid. Yeah, I did do something stupid. I forgot little something, right? Square root. Whatsoever you do unto the left, you shall also do unto the right, right? So to get rid of the x squared, you have to square root both sides. That's because maths is all about equality. What does the square root of minus 1 mean? Didn't we just talk about this? The square root of a number is asking, what number by itself, multiplied by itself, gives me this? Can you multiply any number by itself and get a minus 1? No. Unless maybe they have another department in Bunnings for doing that stuff. Oh, cool, -1. Right? So, and also no square has a negative area, right? That doesn't make sense. So what the heck is going on here? What's going on with this little problem? This issue was bumped into for centuries by math people solving little algebra problems. And you know what they used to do when they would bump into this? Chuck it. It's junk, it's garbage. They just throw it away. This doesn't make sense. Until about the 1700s, a fellow named, let's see if I can get his name up here, Wessel, he talked about this, and he said, this is like a visitation from another world. Does anyone recognize this cat? Yeah, it's like from an Alice in Wonderland, right? Numbers. Maybe there's a need for a new number that can do these things. So natural numbers. I like pie. When I go to lunch, I often take a pie. Go to work and take a pie for lunch. Sometimes I have 1, 2, 3 pies, depending on how full I am. And then sometimes I forget to take pie, so I borrow a pie from my workmate. Can I borrow a pie? So I'm in debt for a pie, for 2 or 3 or 4. And then sometimes we have pie together, so we cut it into 4ths or 3rds, and so we have ratios of pie. And since we're both mathematicians, we just like pie. So notice the sequence. Numbers have grown, the kinds of numbers, and the number systems, partly to deal with problems. Negative numbers weren't accepted until the 1700s. So for this thing to have a solution, there's no real number that solves this, nothing that makes sense to us. Maybe we need a number that multiplied by itself solves this, whatever it is. Like an Alice in Wonderland number. So some guy said this, let I squared equal -1. And this idea was mocked and ridiculed by Rene Descartes. These cannot be real, they are imaginary. Right? They can't be real. And indeed they can't. There's no real number that can produce this result. Until it was defined, this simple little problem could not be solved with any number considered real. But what is this thing? So Wessel, a Dutch surveyor in the 18th century, he significantly contributed to understanding that the real number systems that are so familiar to us, that give us length, quantity, area, are actually a subset of a larger world of numbers. This is what he did. So he started with the real basic stuff. 1 times 1 equals 1. Do we need to discuss that, debate that? Okay, good. So he just arranged these along a number line, but in a plane. And he reimagined the rules of multiplication that were pretty much just taught in primary school. It just is. That's just how it is. And he looked at it as additions of angles. So he put +1 at 0 degrees. And he considered adding 360 degrees the same as multiplying by 1. If you add 360 degrees to something, you get back to where you started, right? And he considered that that's the same as 1 times 1. Then he did something similar too with 1 times -1, where he added, to get to -1, we need how many degrees? 180. There you go. If we want to get back to +1, how many degrees do we need? Well, we're halfway around the circle. How many degrees do we need to get back to what? Another 180. So if you add another 180, that's the same as multiplying -1 times -1 gives you +1. So this is just another way of viewing something that we're all just told in primary school. Right? +1 times +1 gives you what? +1 times -1. But so what happens if I go 90 degrees? That puts me up here, yeah? What number could that be? That's what he called I. Let's call it I. 1 times I equals I. Now what if I add 90 degrees to this? Where am I going to end up? I'm going to end up at 180 degrees, or -1, right? So this is now, by definition, with I being 90 degrees, it's the same as I times I equals -1. How's everybody doing? Right? So just mapping these multiplications over into rotations, addition of angles. Oh, is that the I'm out of frame jingle? Okay, sorry guys. We just did it though. We just showed I times I equals minus 1 and using these rotational things. So what happens if I add another 90 degrees to this? I'm going to end up there. Well, if that's positive I, what do you think the one at the bottom should be? Now come on with confidence. Negative I. So minus 1 times I equals minus I. And then to get back to 1, I need another 90 degrees, and that's the same as minus I times 1 times I equals 1. So we just traversed through a circle of multiplications. Nothing fancy going on here. Just adding these angles. These numbers here are called the reals. Those are the numbers that we know. And these numbers along this axis, they're weird. Right? Those are the imaginary. And in fact, if you took this plane and you rotated it, so you're just looking at this end on, and you're going through these gyrations, you're just going to see numbers go from minus 1 to plus 1, minus 1 to plus 1. And it's not until you rotate it back and you see, oh, when you look at it top down, you're cycling through another dimension. These are known as complex numbers. Yeah, they are complicated, right? But also they're two-dimensional numbers. They're a higher dimensional number system. And it turns out that the number system that we're used to, the ones that make sense with length, area, weight, they're just reals, and they're just embedded in a larger world, a larger dimension. So when you go back to this and we say there's no real solution, that's because the number system that we were using is inadequate, right? Remember how there's no intersection here. It's not crossing the x-axis. In order to see where that crosses the x-axis, we have to expand the numbers into a higher dimensional space. And when you look at this higher dimensional space, you see where they intersect. I trust the psychedelics are distributed in the tea and coffee this evening. Real numbers are a smaller part of a larger world of numbers. Does anyone get excited about that? Yes. That's so awesome. Yeah, usually the response I get is, who cares? I don't care, Shawn. Why should I care about this stuff? Oh, it's on the test. Okay, I care about it until I survive the test. And then I move on with my life. I don't have to deal with this stuff anymore. Well, the mathematicians are quite happy, right? There's no longer unsolvable algebra problems, right? You can always get a root for a problem now. There's no hidden door, forbidden numbers, don't go through there. Complex numbers, they're going to devour your face. Right? That's what I tell my students. Numbers are complete. They're considered done. Are they real, though? Is there any connection of these imaginary numbers to the real world? Materialists believe that mathematical objects exist only materially in our brains. And from an evolutionary perspective, Yehuda Raab describes this rather poetically. Mathematics ought to be viewed as an ever-expanding mansion floating in space, a castle in the air. Constantly new links growing between previously separated compartments. Mathematics is a product of human imagination grounded in our experience with the real world and functions like a language. If you can imagine maybe a little tether tenuously holding this giant castle in the air trying to escape. Thinly connected to reality. Recall the fictional view of mathematics, that mathematical objects are just inventions, right? And this resonates with this whole description as a language. And it's weird. It's like an Alice in Wonderland thing. What the heck does this thing mean? How is this connected to reality? Math has its uses for builders, to keep straight buildings, right? So they don't collapse on our face. So that nurses don't kill us when they inject us with things that we need, right? And perhaps only appreciated by the true practitioners, right? So mathematicians running off and doing these weird things. Evolution may be alleged to create our ability to do maths, but the emergence of gifted mathematicians may be like gifted artists. A mathematician, like a painter or poet, is a maker of patterns. The mathematician's patterns, like the painters or the poets, must be beautiful. Beauty is the first test. There is no permanent place in the world for ugly mathematics. So how do you think that made me feel about my article? This is ugly. An issue of the mathematical intelligence are asked readers to rank mathematical theorems in order of not their accuracy, not their power, not their usefulness, but something else. Any takers? Their beauty. Beauty in mathematics. So for those of you that can't read all these, any square matrix satisfies this characteristic equation. Oh, Or the number of primes is infinite. Oh, Shawn. Yeah. Okay, so we'll take a vote later. You can write down your preferences, right? What's that saying? Beauty's in the eye of the beholder. Excuse me. So the winner is this. This was voted the most beautiful formula. E to the I. That's a great look, Nikki. Oh, what the heck is that? It combines critical numbers, critical values in mathematics. The natural number e, the imaginary number I, the circular constant pi, and the binary 0 and 1. You can assemble pretty much any number you need out of these. Also puts them in a nice tight relationship. This e to the I pi is correlated with -1. Remember those rotations? Pi is 180 degrees. You're sitting at -1 plus 1 equals 0. That's just a rather mathematician's way of saying -1. So I'll give you a moment. Catch your breath. It's okay. It's beautiful, baby. Okay. So we have imaginary numbers winning this beauty pageant. But again, what is its connection to reality? Right? How is it useful? The categories and modes of perception of man's cognitive apparatus are the natural products of phylogeny, and thus adapted to the parameters of external reality in the same way, and the same reason that the horse's hooves are adapted to the prairie or the fish's fins to the water. So they're no different than like teeth, fangs, feathers, fins. Purely utilitarian, right? So purely practical. The logical structure of the universe allegedly guided evolution to man's logical ability. Logical schemes in the coordination of actions, that is, cause and effects, along with physical realities, gravity, inertia, friction, are equated with logical deductive powers. Bob, the mathematician. Such ability apparently includes aesthetic appreciation of fictional entities. Somehow natural selection operated on these abilities during periods of latency. And these fictions result in strange entities disconnected from reality. Strange. We could end the story there. Well, how are we doing for time? What's the time? I do like the sound of my own voice, and all you poor people are still here. We could end it here, but for one little detail. May I introduce you to Schrodinger's equation? Oh, I get some fans. Oh wait, was this from George the other night? He talked about quantum mechanics, right? Quantum mechanics, yeah. So this is a description of quantum mechanics, Schrodinger's equation. Solutions to Schrodinger's equation describe not only molecular, atomic, and subatomic systems, but also macroscopic, possibly even the entire universe. Although I think Wikipedia is being a bit exaggerated. But if you look at that equation, who's sitting in there? I am. Me! Oh, no, the imaginary I. Right? So we got Planck's constant, and behold, the imaginary I is sitting there in this equation. Now, there was some debate as whether or not it needed to be there, because in many ways it's a notational convenience for rotations, right? You can have that e to the I pi stuff. But it turns out that some recent work showed that actually you need these. If you use real numbers alone, it fails. Let's kind of go back to those papers. So I thought it was amazing just to see quantum theory based on real numbers alone can be experimentally falsified. Imaginary numbers could be needed to describe reality. It looks like it has to be in it. It's not just a matter of convenience. This story just keeps getting weirder. Right? If quantum mechanics is correct, imaginary numbers are a necessary part of the mathematics of the universe. That describes everything. That little equation. And who's sitting inside that equation? It's very strange that mathematicians are led by their sense of beauty to develop formal structures that physicists only later find useful. Physicists generally find the ability of mathematicians to anticipate the mathematics needed in the theories of physics uncanny. It's as if Neil Armstrong in 1969, when he first set foot on the surface of the moon, had found in the lunar dust the footsteps of Jules Verne. Eerie. This happens a lot, where mathematicians construct things and do things that turns out a century later. These are really useful for physics. good, right? Although some of the pure mathematicians, they don't care. But what does this say about like fictionalism? Are all these just figments of our imagination? I note that many mathematicians I know are not fictionalists. These connections and the mathematical objects inspire belief in their existence. Beale said that most mathematicians believe that numbers, equations, perfect circles, and so on exist in some ideal abstract sense. But that itself, its existence causes problems. Okay, what if, by some bizarre ability, I was able to transport myself back in time and destroy I? Kill Wessel. You'll never have I. What would happen to the universe? Would it blow up? Goodbye, there's no I. No universe for you. Right? I mean, I can destroy the concept of I. I can destroy the written letter I. But it won't change the universe. Right? Have you ever heard that phrase, the map and the territory? The map of Auckland is not Auckland. Right? There's a distinction between these two. Thank goodness, because if I crumbled that up and threw it in my pocket, and you see the entire city go, ah! There's something amiss. Not sure what it is. Furthermore, erasing all the results for the Pythagorean theorem throughout history will not change the relationship a squared plus b equals c squared. Thank you. Thanks, guys. I do that to my students a lot. I also make them laugh at my jokes. This problem was grappled with by philosophers all over the place, right? The laws of number are not really applicable to external things. They're not the laws of nature. No, they're the laws of nature. The laws of nature. The universe has a mathematical architecture. Scientific laws we've encountered, characterized, codified, are structured and describable in mathematical terms. The fact that the universe obeys mathematical laws has not been lost on many brilliant minds over the centuries. Philosophy is written in this grand book, the universe. It's written in the language of mathematics. Its characters are triangles, circles, geometric figures, Galileo. Fast forward to the 20th century and the famous theoretical physicist, Richard Feynman. I find it amazing. It's possible to predict what will happen by mathematics, which is simply following the rules which really have nothing to do with the original thing. There's a disconnection, and yet there isn't. What the heck is going on? I think it's cool. Evolutionists typically claim that our logical capability evolved as a result of the logic in the world, and others find this unlikely. A great mathematician fully, almost ruthlessly exploits the domain of permissible reasoning and skirts the impermissible. That his recklessness does not lead him into a morass of contradictions is a miracle in itself. Certainly, it's hard to believe that our reasoning power was brought by Darwin's process of natural selection to the perfection which it seems to possess. Remember Bob, the mathematician? What sort of survival skill set does he have? Bob's a nice guy, but don't give him a car. Right? I mean, we have an intuitive sense about the way the world works, right? But our logic leads us into these completely counterintuitive, bizarre things like imaginary numbers. Even just negative numbers were rejected for so long. But also its resonance with our thinking, our minds. The profound interplay between the workings of the natural world and the laws of sensitivity of thought. An interplay which, as knowledge and understanding increase, surely ultimately reveals a deeper interdependence of one on the other. We can do math. That alone says something curious. Evolutionists would have it that there are no truths. There are no preordained, predetermined mathematical truths that just lie just out there, up there. Evolutionary thinking teaches us otherwise, but that's not what we see. The universality of mathematics is suggested by the fact that mathematicians widely separated in space, time, and culture find the same thing. It's not an accident. A squared plus b squared. C squared. Thanks, man. Bertrand Russell, certainly no friend of theism, concluded from his study of the history of Greek philosophy that mathematics is the chief source of the belief in the eternal and exact truth, as well as in a super-sensible, intelligible world. They're all distinctly mathematical, some even profoundly counterintuitive, some hinging on mathematical objects that we would reject, some so far removed from our everyday experiences, and some ugly. I don't know why I showed this off. I should find something else ugly, because that's mine. I'm a bit ashamed. Shawn's ugly maths. But so, why is it ugly? We have an appreciation for simplicity. Simple, elegant solutions. If I have a simple task to perform and I create some crazy Goldberg device to accomplish a very simple task, would you use this Goldberg device to light a candle? Oh, but it's so much fun. I love watching the balls roll around. But what if you're in a hurry? You need to get this done fast. Is there a simple way of doing this? Strike a stinking match and you're done. Good grief, Shawn. You and your Goldberg device. It goes for maths as well. In fact, simplicity is used as a guide for finding mathematical truths. One of the most important things in this theoretical physics business is to know when you were right. It is possible to know way ahead of checking all the consequences. You can recognize truth by its beauty and simplicity. Beauty and simplicity leads to truth. What a profound statement. Here we see a renowned mathematical physicist equate truth with aesthetics. And these were instincts honed over a long and very successful research career, and in no way limited just to Richard Feynman. I'm going to read a little story to you, so I'm going to drink first. Lemonade. I was thus led to a long calculation. The longest in my career, full of local tactical tricks, the calculation proceeded by twists and turns. There were many obstructions, but always after a few days, a new trick was somehow found that pointed to a new path. The trouble was that I soon felt I was in a maze. I'm not sure whether, in fact, after so many turns, I was anywhere nearer the goal than when I began. This kind of strategic overview was depressing. Several times I almost gave up, but each time something drew me back. Usually a new tactical trick that brightened the scene, even though only locally. Finally, after about 6 months of work off and on, all the pieces suddenly fitted together, producing miraculous cancellations, and I was staring at the amazing, simple final result. And these are the words of the Milkville Prize laureate Chen Ying, describing his personal experience, exploring reality through math. And I've had a taste of it. I'm not going to get a Nobel Prize. Not anytime soon, if ever. But I've had a taste of it. Back when I did real maths, when I did my master's, sometimes we would do derivations, pages and pages and pages and pages. It was insane. There's no end. Will I ever be free? And then at some point, bring in something, multiply by this part over here, this part over here. All these cancellations. That was amazing. Right? It's like, that's so cool. And then you have this sense, I'm on to something. I've got it. You grab onto it and you pull. And it turns out, yeah, I got it. It affects you. And it's strange. It's clear that Yang's confidence in his calculation is bolstered by the miraculous cancellations he experiences. But such thinking is anthropocentric, even childlike. What has miraculous simplification of the notation we use in describing nature got to do with nature itself? Why would that sense lead us to truth? Representations of biological mechanisms can be quite ugly indeed, and some can be simple. This is a simple recursion formula. Out of this simple little formula, where you start with a number, you do something to it, you plug it back in. You just keep doing it again and again and again and again, and you get this. You can get fantastic complexity out of the simplest little expressions. It might take a while to do it. What did he say? 4 weeks. And a lot of these fractals, as they're called, this is the Mandelbrot set of fractals, the mother of fractals. They're used to describe many things in reality, and in some parts we're not quite sure how to use them all or what all they mean. But one of the truly amazing things to it is that the deeper you dig into the Mandelbrot set, eventually you end up where you started. Freak show. But throughout biology, there are these beautiful patterns that are generated by such simple things. Does anyone recognize this thing? Fibonacci. Right? This is just a simple sequence to generate these complex patterns. You just take the previous two numbers and add them. 1 plus 1 gives you 2, 2 plus 1 gives you 3, 3 plus 2 gives you 5, 5 plus 3 gives you 8, and you just keep generate amazing complexity out of such simple patterns, simple relationships. We see this all over the place. It's not limited to Fibonacci or Mandelbrot. Schrodinger, Newton's laws. What's the last one up there? Some fellow named Einstein, right? He cooked that bit up. Right? What about this one? Maxwell. I heard Maxwell. Maxwell's equations that relates electricity and magnetism. Thanks to him, we have Wi-Fi and cell modems. What is that other one? The one in the middle. A squared plus B squared equals C squared. Thank you, guys. And then what's this one here? That's the most what theorem? Beautiful. I heard beautiful. I think I heard beautiful. Okay, thank you. Most beautiful. Man, that thing's gorgeous. And so we also have Mandelbrot set. And what? Oh my. Your test for the day is naming this happy little character. Does anyone remember this? Does anyone remember waking up screaming while taking out? What is this thing? I hear quadratic formula. Thank you. Thank you. I think we should get t-shirts printed up so people can proudly wear the quadratic formula at parties. Keep going. I can find roots. What? What does it mean? All these universal facts, relationships are all over the place. Does it mean something? Has anyone used software they don't have a manual to? All the time. So you get apps on your phone. Well, back when I was at Sandia Labs, I had to visualize some of the 3D simulations that I did. They had some in-house software that I used. It didn't come with documentation, so I had to ask people around me, hey, how do I do the thing with the thing? And oh, you just go over here, you push this button. Oh, I guess wait. And then, hey, how do I solve this? And how do I get this? Oh, you just do this. And eventually I exhausted the knowledge of everyone around me. I noticed, oh, at the top, there was a button that said help. So I clicked on it. You know what it did? It popped open a window that said, are you kidding? Oh, okay. And it went away. So I used something else. Was there a presumption in my using that software? That it wasn't written by a crazy person? Right? That there's a logic to it. That's what you're doing when you're trying to sort out, how does the software work? Was this written by a crazy person? Right? Any mechanics in the room? Oh, a person brings in a car. It's like when I turn the wheel this way, it makes this weird noise. And so you go and you start diagnosing it. How do I fix this thing? What's the presumption under this? That it wasn't built by a crazy person, right? There's a logic, there's an order, there's a structure to it. What about doctors? When a patient comes in, when I move my shoulder, it makes this weird noise. Right? So they diagnose, right? Put oil on you and jack you up. We'll fix this guy. Oh, your drive belts are shot. Right? But when they're trying to treat you, there's a presumption. There's a logic. There's an order. There's a structure that you weren't made by a crazy person. This thing called math. It's useful. It's beautiful. It has a simple expression, like a visitation from an alien world that describes everything. Why? Why this intimate connection to reality? Why this connection to our minds? Why can we do it? The philosophers have discussed this to no end. And I've trimmed this down significantly because philosophers are the opposite of mathematicians. They use lots of words to say little things, and mathematicians use very few symbols to say lots of things. Did you get all that? For a non-theist, realism that mathematical entities exist in another dimension, a philosopher of mathematics, Mary Lang, points out the fact that physical reality behaves in line with the dictates of mathematical entities existing beyond space and time is a happy coincidence. Hooray! Don't you feel lucky? By contrast, a theist can argue that God fashioned the world on the structure of mathematical objects. This is basically what Plato believed. The world has a mathematical structure as a result. It made it that way. For fictionalism, that these are just inventions. Lang says that on empty realism, relations amongst mathematical objects just mirror the relations amongst things in the world, but remains wanting, is why the physical world exhibits such a complex and stunning mathematical structure in the first place. It was equations. A theist. The world exhibits this mathematical structure because God chose to create it that way. This was the view of the Jewish philosopher Philo of Alexandria. God created the physical world on the mental model in his mind. And I might ask you, what God are we talking about? Remember this fellow? H.P. Lovecraft. American author of extraordinary horror. And now his name is used to describe versions of horror, Lovecraftian. A theme throughout his works. Forbidden, dark, esoterically veiled knowledge. Many of his characters are driven by curiosity or scientific endeavor, and in many of his stories, the knowledge they uncover proves Promethean. Filling the seeker with regret for what they have learned, destroying them psychologically, or destroying the person who holds the knowledge. Lovecraft believed in a purposeless, mechanical, and uncaring universe. Human beings with their limited faculties could never understand the universe, and the cognitive dissonance caused by the revelation led to insanity. At the center of Lovecraft's world was a god, Azathoth, a god of madness and chaos. A completely incomprehensible universe, a reality that would just drive us insane if we saw it in all its power and glory. But we don't see that. We see a user-friendly universe. Thank goodness. You find it strange that I find the comprehensibility of the world as a miracle or an eternal mystery. Well, a priori, someone should expect a chaotic world. This cannot be grasped by the mind in any way. The success of such a project, science, presupposes a high degree of ordering of the objective world. This is a miracle which is constantly being reinforced as our knowledge expands. Albert Einstein. One of the most important things in this theoretical physics business is to know you were right. It is possible to know way ahead of checking all the consequences. You can recognize truth by its beauty and simplicity. Has Feynman answered Pilate's question, what is truth? Of course, I'm a theist. Truth is staring at him in the face. I am the way, the life, and the truth. And of course, we made in the image of God, we have the capacity to do what? To run away, to do math, to varying degrees, to predict things about reality. Math is a language. It describes relationships and quantities in the world precisely. A game with logical rules of deduction and construction. It's related to the intrinsic architecture of the universe. It was made that way. These alien constructs of the game lead to profound revelations about the nature of reality. It is a distinctly human endeavor. Universal ideals, beauty, simplicity lead to truths about reality. And the solution is very simple and divine. So I am from New Mexico, and I've noticed the years that I've been in New Zealand, the Mexican food is terrible. So I torture you with a picture of the best food in the world. New Mexican enchiladas. And also that's the view of the Rio Grande Valley where I grew up as a child from New Mexico. Thank you, everyone, for coming out and enjoying, hopefully, a little talk about math. Wow.
So much, Shawn. Fantastic. I don't know if you want any questions.
Yeah, does anyone have questions? Do we have time?
So go.
I do like the sound of my own voice. Yes, ma'am.
What sort of things have you discovered about the gut and maths?
About the gut with maths.
Yeah.
Oh, I just kind of mentioned it a little bit, but mathematical biology basically comes down to making a bunch of very complicated expressions to represent some behavior in a biological system, and then you run to a computer and you hope it solves it. And so you run lots and lots of simulations, and you change parameters, and you see what you get. So you try to fit models to experimental data, and then try to make some predictions. We don't really have any fundamental relationships like E equals MC squared or F equals MA. So the things that I did discover along the way, most of it's very incremental. What I found out is that you need calcium. So throughout your guts, there are these cells that they generate steady contraction signals. There's a whole network of them. And that the way that they generate these signals is with ding, calcium. Right? And also calcium is, that's the primary thing that I studied in cell biology. So in neurons, you need calcium in order for neurons to fire. You need calcium in your muscle cells, your heart cells, your smooth muscle cells for it to contract. Without calcium, you don't do a thing, right? You need calcium. Calcium does a body good, right? So I guess that's what I discovered. You have a question, don't you? No? Okay. You just look so expectant. You wanted to say something.
Well, my father was a PhD in plant biology, a lot of research on it, yet he was
Oh, okay, yeah.
never saw the connection.
Oh, well, it's not, of course I have many atheist friends, but so one of them, he did his PhD in genetics, and it was amazing to me how one time he came home and he's like, you know, when you're watching a cell and it's doing all these things under the microscope, you can't help but wonder who's running the show. Anything else? Any other questions? Any comments? Arithmetic errors? 2 times 3 is 6, Sean, not 5.
What is your process for breaking down complexity to solvable problems?
Oh gosh, with biology it's disgusting. Biology is disgustingly nonlinear. I don't mean just wet and sticky. Right? But so from a mathematician's perspective, there's this constant battle between biologists that think everything is relevant. And I have a paper in review right now that maybe I'm getting too excited. Right, so I reduced a model. I took a model of a uterine smooth muscle cell and I reduced it, I simplified it. I can take my smaller model and reproduce the exact same data that someone did with a huge complicated model. So I was proud of myself. And it comes back from the reviewers, what have you done? This is useless. But I was able to minimize the model. So sometimes what you do is you have to take other people's work, look at it, break it down. This part is necessary, this isn't necessary. Sometimes it's just a matter of turning on and off things and playing with it for a while. But also it says a lot about how, in biological systems, I've mostly been studying cellular, there's so many mechanisms in there that don't seem to be doing that much, right? So one of the things with the model I reduced, it had tons of mechanisms in it that I chucked. I was like, we don't need these. I can just use this mechanism and it represents all that other stuff. And one of the complaints was, you've lost biological realism. And so of course my counterpoint is, well, because they're not biologically relevant. Right? So that's a huge part of like the mathematician's approach, is to simplify. What's the smallest, most simple, compact way of representing this behavior? That's what I did. So I suspect the reviewers were biologists. But so sometimes there are mathematical analysis techniques. So I actually used a different technique called steady state approximations. Does that sound familiar to anyone? So just looking at timescales. So some of the timescales are so fast. And the timescales for the behavior we're interested in are much longer. And so I'm like, why are we killing ourselves solving these really fast things? We can just assume they're done. That's what steady state approximation means. You don't solve the kinetics, you just go bang, it's already done. Do we want to go into bifurcations? We could wheel out a whiteboard. I can see some of you are excited. Oh yes, please, bifurcation. Hi. Anything else come to mind? Anything? Should we call it there? Because there's cake. There's quite a bit of cake. So the guys, they brought an amazing setup tonight. So I actually want to thank Disney and the Calvary Chapel gang. Thank you guys. Woo-hoo, cake. Well, thanks again for coming out, everyone.